Well, I'll begin with a word of prayer. Dear Father, we thank you for this day, and I thank you for this class, and just ask you to bless our work today. Help us to understand a little bit more about how to solve differential equations with series methods, and just pray that you would aid our understanding, Lord. In your name I pray, Lord Jesus. Amen. All right, so this next solution technique is exciting in some sense because it's so boring. And what I mean by that is, like, the method pretty much is just the following. To solve a differential equation using series, simply assume that your solution is a series, plug it in, and work it out. So let's look at some examples. So today I want to show you basically the method and the major theorem about the extent of the domain of solutions. I'm going to start out with some relatively easy examples which don't require this sort of full analysis. So we'll start out with, say, y prime prime plus y equals to e to the x squared. All right. My goal here is to find solution centered at x equals to 0 to order 4. All right, to order 4. And so the way this is done is to assume that the solution has the form of a power series centered at 0. A power series centered at 0 is simply this. Y is equal to, say, a sub 0 plus a sub 1 times x plus a sub 2 times x squared, a sub 3 times x cubed, a sub 4 times x to the fourth, plus dot, 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 dot. So that's all we need. Now we differentiate this, and we get a1 plus 2a2x plus 3a3x squared plus 4a4x cubed. And then we differentiate a second time, and that gives us y prime prime equals to 2a2 plus 3a3x squared plus 12a4x squared plus dot, dot, dot. All right? Great. Now I want to plug that into the differential equation. But in order to be fair here, I also should probably expand e to the x squared as a series. Yes, sir? Yes, thank you. Very helpful. Much appreciated. Anything else? Okay. I've done horrible things in lecture today, so I'm capable. There's no bounds on the. I could do horrible things today, so keep an eye on me. Yeah. What I was just saying. Thank you. There we go. See my previous comment? I'm not working with a full deck today. I don't know what happened. I got plenty of sleep. It's just that day. So, all right. So this is what my twice differentiated abstract solution looks like. On the flip side, I need to convert e to the x squared to a series. So I would remind you, we have the Maclaurin series to work with here. So this is 1 plus x squared plus 1/2 x to the fourth plus dot, 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 right? I am reminding you e to the u is 1 plus u plus 1/2 u squared, 1 over 3 factorial u cubed, and so forth and so on, right? So this is a known Maclaurin series from Calculus 2. I'm simply substituting u equals x squared into that series. And that ought to be enough, because that's order 4. All right? Now I put these two things together. Simply put these two things together. And what do we have? We have, let's see here, y prime prime. I'm going to write it out here. We got y prime prime plus y equals e to the x squared. All right, great. So what does that give me? That gives me 2a2 plus 6a3x plus 12a4x squared plus dot, 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 plus I'm going to write it on the next line if that's okay with you guys. A0, even if it's not, I'm still going to do it. A1x plus A2x squared plus, I'm going to stop right there. Maybe just writing out terms to x squared is enough, right? So this is y prime prime, this is y, this is all supposed to be equal to 1 plus x squared plus 1/4 x to the 4th, all right? Yeah? Okay, so we've got two series that are equal, right? What we're going to do now is to equate coefficients, all right? Equate coefficients. Now, how's that go here? How about constants? What do we got for both sides? I got a 2a2, right? Plus what? Plus a sub 0, right? That's it for the constants on the left-hand side, yeah? On the right-hand side, what's my constant? 1, great. How about x? X, we got ourselves a 6a3 plus a1 equal to, what's my coefficient of x over here? 0, yay. All right, how about x squared? What do we got from that? Looks like we got a 12a4 plus a2 is equal to 1. All right? So what I anticipate here is that we can write everything in terms of two constants, right? So why am I expecting that? This is a second order differential equation. We should be able to find basically two solutions, and the solution should look like, what are we expecting here? The theory still holds, is my point to you guys. So we're expecting that y is equal to like c1 y1 plus c2 y2 plus a particular solution. All right. So like this is what I'm looking for. I'm looking for this to happen, right? And I expect there are going to be two constants in the solution, right? And if you look at this, you should see that we could solve for a2. a2 is equal to 1/2 of 1 minus a sub naught. All right? And check this out. I can solve for a sub 3. A sub 3 is minus 1/6 a sub 1, right? And the x squared equation, I can solve for a4. a4 equals to what? Looks like 1/12, right? Of 1 minus a2. And that's all I need. That's all I need. See, because I'm only trying to find the solution to order 4. Now all I need to do is put the red equations back into my initial solution and just understand what we're looking at. So let's finish it here. So y is equal to a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th. But in detail, that is a sub 0 plus, what is my a1? My a1 is 1/2 of 1 minus a0 times x. And then I've got my a2, which was 1/2 times 1 minus a sub 0 x squared. Then my a3 was minus 1/6 a1 times x cubed. I'm just substituting in the red equations into the general format here. a4 is plus 1/12 1 minus a2 times x to the power 4, and then it goes on. Yeah.
Why are the a1 and a2 terms?
Oh, I think it's because I made a mistake there. I warned you I was going to do this. It's easier than this, isn't it? What can we do here? This is actually what? No. A1 is just A1. It's more boring than that. Thank you. Very helpful. For the record, I think I just made it 90 seconds without a mistake, so that's good. Let's see if I can make it another 90.
And does that mean the 1/6
Well, my A2 is 1/2 1 minus A naught. My A3 is equal to minus 1/6 A1. A4 is 1/12. I think it's okay. So like, just to do some color coding, guys, this is A2, right? So I'm replacing this term right here with that expression, okay? This is my A3 formula. So I'm taking this term right here and I'm replacing it with that, right? Let me find another color. A4 is this, so I'm replacing that with that. All right, so let's clean up the solution. What we got? So if you look at this, I have a sub 0 times what? Times 1 plus 1/2 x squared. All right. Oh, that feels wrong. Oh, why is that wrong? I shouldn't have a 12 there. I should have like a 24. Oh, I'm not done. I'm an idiot, guys. This isn't done, right? I want to have everything in terms of, want to have everything in terms of A0 and A1, right? So the thing I just underlined in brown, I'm not quite done yet. What should I do here? Well, I should plug in A2, yes. So this is 1/12, 1 minus 1/2, 1 minus A naught, all right? And if I do that, I get 1/24, I think, plus 1/24 a sub naught. I think so this inside here, I get a 1 minus a half, which is a half. A half times the 12th is a 24th. And then the other term, I get a plus a naught over 2, which when multiplied by the 12 gives me 1/24. So thank you. So I've got 1/24 plus a sub 0 over 24. All right. So this should have been 1 over 24 x to the 4th. And you guys tell me, there's another error I just made here. Can you guys tell me what it is? I'm factoring an a sub naught out. Minus 1/2. Minus 1/2 right there. Minus 1/2 x squared. Now I've got plus a1. And what I should get is x minus 1/6 x cubed plus dot 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 dot. And then plus what? The terms without constants, namely 1/2 x squared plus 1/24 x to the 4th plus dot dot dot. Yes?
When we built those three-part equations, why do they have to be in terms
When we built the what equations?
on the right? Those three equations in red.
What about them?
Why do they have to be in terms of A0 and A1?
Why not? I mean, the reason for that is because A0 and A1 have an important significance to the solution. What's their meaning? What is A0 to the solution? Do you remember Taylor's theorem? Taylor's theorem says that y of x, right, is equal to the sum. Here's Taylor's theorem at 0 anyway. Sum n equals to infinity, n 0 to infinity of the nth derivative of y at 0 over n factorial, right, times x to the power n. This is Taylor's theorem for y at 0. So what's the meaning of y0? What's the meaning of y of 0 is what? Check it out. Y of 0 would be equal to a sub 0. Y prime of 0 would be equal to a sub 1 if you compare. So that's part of the reason I'd like to do that, is that if I rewrite it in terms of a sub 0 and a sub 1, those have the meaning of initial position and initial velocity. That's a good question. Here's a deeper question. Could you solve for, could you use some other choice of the parameter? Could you do everything in terms of like a sub 2?
Probably could.
Could, but do you want to? I mean, No, I think so. As a matter of convenience, I usually try to pick the lowest two non-trivially appearing coefficients to use as parameters in the solution set. Now that has had a nice effect here. Can you guys recognize what we're looking at? What is this? What's this? What's that? Yep.
When you have 2, 1, 24 x to the 4th, this is supposed to be 1 over 24.
What do you mean?
At the end, you have 1 over 24x to the 4th.
Yeah.
You have the same thing in A naught.
Yeah, there's two of them though. I've got the 1/24th without the A naught, and yeah. So the without the A naught is the part that goes into the particular solution. Part with A sub naught is the part that goes into the homogeneous solution. Can we recognize this is cosine x? What's the other one? Sine x, right? This should be completely unsurprising. This is a constant coefficient differential equation. What are the homogeneous solutions? Sine and cosine, right? What did we find? Cosine and sine. And then this piece over here is what? This is my particular solution, right? All right.
Would the A naught and A1 be kind of classified as C1 and C2?
Right, yeah, the A naught and A1 are the constants that we need to formulate the homogeneous solution. Example 2, suppose we have y prime prime plus e to the x y is equal to 0. Find solution to order 3 centered at x naught equals to 1. And let's give ourselves a little bit more data here. Let's assume that y of 1 is equal to 2, and y prime of 1 is equal to 3. All right? So this one's a little bit different than my first example, because now we've got a homogeneous problem, right? And can we solve this thing using our previous method? Well, I guess that's a good question. The first example, could we have solved that with our previous method? I would say no, because e to the x squared is not something that we can annihilate, right? And if you think about variation of parameters, it would be integrals that you just don't want to do, right? Like pretty much the only way to solve those integrals is to use a series technique. All right. Okay, so what's our deal here? So here we're centered at x not equals to 1. What does this mean? This means we want to write our solution in the form the sum n equals 0 to infinity of like a sub n times x minus 1 to the n power. All right. That's what that means, centered at 1. So we have y is equal to a sub 0 plus a sub 1 times x minus 1 plus a sub 2 times x minus 1 squared, and so forth, all right? So we differentiate, well, before we even differentiate, can you guys tell me what that is then? Y is equal to what? What did I tell you in the problem statement? Y of 1 is 2, right? What happens when you plug put x equal to 1 into this formula? Everything here is 0, right? The only thing that's left is a sub 0. So this a sub 0, of course, is 2. And a sub 1, by a similar token, is 3, right? Because again, the meaning of the 0th, this is equal to, if this is equal to f of x, right, then that's equal to f of 1 plus f prime of 1 times x minus 1 plus 1/2 f prime prime of 1 times x minus 1 squared plus dot, 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 right? Taylor's theorem. So Taylor's theorem says there's a relation between the derivatives and the, the values of the coefficients. So I know that this is a 2 and a 3. If you guys don't mind, I'm just going to erase and put 2 and 3 there. Save myself some writing. So I got a 2 here. And I've got a 3 here. All right. Now let's differentiate. So what's y prime prime? I'll do y prime. So we've got what? We've got 3 plus 2a2 times x minus 1 plus 3a3 times x minus 1 squared. And then y prime prime is 2a2 plus 6a3 plus stuff, right? I think I'm missing an x minus 1. All right, let me step away from the crime scene and see if there's anything I need to be charged with. I should have brought my glasses. Anything? So the method here, guys, is to convert everything in sight to a power series of the kind that you're trying to find. So as you look at the differential equation, great, we've got our potential solution y and y prime prime in the right format, right? But the differential equation itself has got an e to the x in it. So we need to find a power series expansion for that. How do we do that? I guess I'll do it down here. Well, there's a couple different ways. Here's the way I do it. I use a trick. I say e to the x is equal to e to the x minus 1 plus 1, right? Which is equal to e to the 1 times e to the x minus 1, which is equal to e times 1 plus x minus 1 plus 1 half x minus 1 squared plus dot 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 dot. Right? So that gives me a way to expand the exponential, right? So it's e plus e times x minus 1 plus e over 2 times x minus 1 squared plus dot 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 dot. Now, of course, you don't have to do it this way. You could use Taylor's theorem. It's about the same time and trouble, right? Because if you think about the derivative of the exponential function, what's its derivative? Derivative of e to the x is e to the x. Second derivative e to the x, e to the x. Third derivative e to the x. We could be here all day, right? So it's not surprising that the coefficients here, respectively, f of 1, f prime of 1, f prime prime of 1 divided by 2. The 2 is from Taylor's theorem, right? All right, well, let's put it all together. So we're looking at, this time, y prime prime plus e to the x times y equals to 0. All right, so this is, what do I got? 2a2 plus 6a3 times x minus 1 plus dot 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 plus parentheses here, e plus e times x minus 1 plus e over 2 times x minus 1 squared. But I think I can skip that. I'm going to skip the third term because I don't think I'm going to get that far. So I'll just keep the first two terms. And then my y was 2 plus 3 times x minus 1 plus stuff. I guess I should maybe include the next term. What's the next term? a2 x minus 1 squared. All of that's equal to 0, right? Now, there's always a question in these kind of calculations, which is how many terms should you keep? Well, that depends on the question. How many are you trying to solve for, right? We can always get more by keeping more. But I think I have enough for us to get the 3 I asked for. So let's work it out. And so this we're going to have to multiply series, but good news, you learned how to multiply series in calculus too. So hooray. So constant. And how do you multiply series? Just like you multiply polynomials, right? You match terms, collect like terms, and that's pretty much it. Distribute. So here we have the constant. I've got 2a2. And over here, I've got this e times 2. And I think that's it. I don't think there's any other potential constant term in that product, right? The only way I can get a constant is from a constant times a constant, and that's the only two constants that there are to multiply, so that's it. So plus 2e is equal to 0, because there's no constant except for the 0 on the other side. What's up next? Well, x minus 1. And what do I have in terms of x minus 1? Well, let's look. We've got a 6a3 from here. What else? All right, so I've got this e times 3. That gives me a 3e. I've also got this e times 2. Both of those are ways I can get x minus 1, right? So I've got plus 2e. I think that's it. There's no other possible way to obtain an x minus 1 power except to take x minus 1 times a constant term, right? But there are two such products, so now there's two things here. The 2 and the 3. That's equal to 0. All right. I think technically speaking we could stop right here. But I'm going to go one more step just to illustrate the method. Maybe we'll get a little bit more than I asked for. That's probably not the worst thing. So x minus 1 quantity squared. We can equate coefficients of that term. Now I haven't written it down, but what would be the next thing that I didn't write down with a4? What would it have been? You can kind of see from the last example, right? The a4 term gets a 12. So we would have had, if we'd continued writing, we would have had a 12a4 times x minus 1 squared there. And then over here, we've got what? We have e times a2, right? We got that one. We've also got the e times 3 plus 3e from this times that, right? Is there anything else to get an x squared? There's also the next thing I haven't written here, right? What would be here if I continued? We'd have what? 1/2 e times x minus 1 squared, right? That was the next thing. So we would have that times this 2, which would have given me a plus e. But that's it. That's the only possible ways you can create a quadratic term. Yes?
If we haven't written them, why do we factor them
Because I'm trying to equate the coefficients of x minus 1 squared.
in? Oh, I misunderstood.
Yeah. Yeah. Uh-huh. I mean, this is a danger of this kind of calculation, is if you think you're going to a certain order, right, and you stop a pattern short, or if you don't think about how another term multiplies to give the order, you can miss terms. That's something to watch out for. Yeah. Was it? Oh, okay. So now we've got our defining equations we can solve. We've got, this tells me a2 is what? a2 is, cancel the 2's, a2 is minus e, right? And what's this tell me? This tells me a3 is 1/6 of minus 3e. Oh, that's a 5e. Let me not be come on, minus 5e. Let me be civilized here. We can add 2 plus 3 is 5, right? So minus 5e. So apparently a3 is minus 5/6 e. E is a number, right? And this tells me a4 apparently is what? This is 4e, so I get like 1/12 of minus ea2 minus 4e, I think. So a4 is equal to 1/12 of minus e times, a2 was minus e, right? Minus 4e. Apparently a4 should be 1/12 of e squared minus 4e, if I haven't made a mistake. So put it all together, we find solution. Y is equal to 2 plus 3 times x minus 1. My a2 is minus e times x minus 1 squared. My a3 was minus 5/6. 5/6, I can't say sixth today. Minus x times x minus 1 cubed. And then plus 1/12 e squared minus 4e times x minus 1 to the 4th power plus dot 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 dot. So There you go. I actually found the solution to order 4 as it happens here. All right. Any questions? Yeah.
If you ask for order 3, and we like get the stuff for order 4, can we just like get rid of it and put that?
Yeah. I mean, technically speaking, this was extra. You didn't have to find that, you know. And you know, time is money on the test, right? So you don't want to do more than you need to, right? But okay, so these are a couple of simple examples. Well, they're moderate examples. My next example. So by the way, if I ask the question, where do the solutions we found in both of these cases, what's the domain of the solution? All right? What's the domain of the solution? That's something we should talk about just a bit. And here's the theorem. If we have y prime prime plus, let's say, b of x, y prime plus c of x times y is equal to f of x, all right? Then the power series solution, let me call this thing star, to star centered at x equals to x naught is as large as it can be without going past any singularities for b of x, c of x, and f of x, viewed as complex functions. This is one of those places where, like it or not, complex variables comes into play, and it's something we need to think about just for a minute. It's not a big deal, but I mean, I'll show you. So, all right, I can pretty much illustrate this theorem with an example. Let's see here. Suppose we have y prime prime plus, x squared, my bad, 1 over x squared plus 9 times y prime, plus, let's say, 1 over x squared plus 16x plus 65 y equals to, e to the x. All right. So this differential equation gets into trouble nowhere in terms of real variables. If you think about real variables, all of the expressions I wrote are defined for all real numbers, because the quadratics that I wrote in the denominators here they're complex, right? I guess I could make this more interesting by throwing in like an x minus 7 over here. Then we lose one real point, right? This differential equation is not defined for x equal to 7 if I do that, right? So it's probably healthy for me to have at least one singular point that's real. So let's throw that into the mix. So you guys, what are the singular points then? What do I mean by singularity? That's just a fancy word for saying that these functions are not defined in the complex sense, right? As complex functions. So like here the deal is x squared plus 9 is x plus 3i times x minus 3i. And x squared plus 16x plus 65 is x plus quantity 8 squared plus 1, which, by the way, is x plus 8 minus I times x plus 8 plus I. So that's what's hiding here. So the singular points are what? We have singularities at x equals to 7 from this guy, right? Is e to the x singular anywhere? No, I mean e to the x, sine, cosine, cosh, these are defined for all reals. So x equal to 7 is a singularity, and also x is equal to plus or minus 3i, those are singular points. And also x is equal to minus 8 plus or minus I, these are singular points. All right? So I can draw a complex plane. So we draw the imaginary axis in the vertical sense, and we draw the real axis in the horizontal sense, right? And I can plot these singular points. I usually use x's for them. So like there's a singular point at minus 8 plus or minus I. So like if this is 8, we've got one here and one there. So this is like minus 8 minus I, minus 8 plus I. Those two. And plus or minus 3i would be like, you know, here maybe, and down here, up to the limits of my artistry. So there's the other two singular points, right? Those are on the y-axis, right? The imaginary axis, really. And my, also 7, right? Let's see here, so here-ish. I tried, guys. I don't think I've been successful in maintaining scale in this picture, but anyway, I tried. Okay, I tried. So the picture is just a mnemonic, though. So what did the theorem say where x naught is? No, it didn't, right? But this single graph gives me a template to answer a host of questions about different potential centers for my solutions. Right? Like let's look at some specific examples and see how the theorem plays out. So like example 3a, x naught equal to 8, right? If I make the center of my solution 8, where's that in this picture? It's like right here, right? What's the nearest singularity there? 7, right? So in this context, what this theorem says is that my solution to star centered at x naught equal to 8 has open interval of convergence and I'm going to abbreviate interval of convergence as IOC because I get tired of writing interval of convergence, but the open interval of convergence would be 7, not included, to 9. Right? The radius of convergence here is what? 1, right? What if I was going to put, what if I made 0 my next one? Example 3b. What's closest? How far is... So my picture is not quite right. I mean, 7. This 3, I think it started... The first mistake was drawing these too far away from the axis, you know? Because certainly, if this is 3, then 7 should be more like here-ish. So it's not... The picture is deceiving. How far are plus or minus 3i from the origin? 3. How far is 7 from the origin? 7. How far are these two? Here we need to think about, what's that? How far is this? What's this distance right here? Can you guys tell me? Square root of what? What's that? Say what? 64 plus 1, right? Because we've got 8 squared plus 1 squared, Pythagorean theorem square root. So square root of 65 is how far that is, right? And is square root of 65, how does that compare against 3? It's more, right? So the answer is, IOC, interval of convergence, for solution includes -3 to 3, right? And I won't draw it because it's too embarrassing. But there's a disk of radius 3 centered around the origin, which that's the only, it butts up against the plus or minus 3 i's, and that you can't go past that, because to go past that you'd cross the complex singularity, all right? So if I solve this, if I find a series solution centered at 0, I only can hope that it converges up to like values plus or minus 3, not included. What happens at 3 is an open matter. It may or may not be included at 3, right? In contrast, over here, the solution definitely doesn't make sense at 7 because the differential equation is not defined at 7. So, except perhaps in a limiting sense. All right, so what's a place where it gets tricky? The tricky case is when you actually have to think about it, which would be something here like maybe -2. What if I have -2 is equal to x naught? So then notice that the distance to plus or minus 3i is what? What's this distance here? You got 2, right? And you got 3. So it's the square root of 2 squared plus 3 squared, also known as square root of 13, right? 9 plus 4, 13, square root of 13. So this is square root of 13 distance. How far is it, on the other hand, down over here to this other one? Like, what's this distance? So how far are we going? What's this? Look at the little triangle here. Did I ever move the camera over here? Oh, man. That's the worst. Sometimes it doesn't matter much that the camera is not pointing at the board. This is not such a time. Well, this was going to be a good video. And on top of things, it's in that window puts a stupid glare on this board. Some places. It depends where you're sitting, it moves. I need to get some aluminum foil and cover that window. So, all right, so this right here, you guys told me we go 6 over, right? And 1 up, so 6 squared plus 1, so square root of 37. So square root of 37 versus square root of 13. My picture is deceiving, of course, right? This is actually closer. Because the plus or minus 3i is root 13, whereas the plus or minus 8 minus 8 plus or minus I is actually a little bit over 6 units away from it, right? So my interval of convergence includes, and here's how it goes. You do -2 minus the square root of 13 to -2 plus the square root of 13. That's how it works. You do plus or minus the distance to the closest singularity. We're guaranteed that much, at least, is going to be solved if we find a solution centered at -2 for this problem. All right? So that's pretty much the method. Yeah, I mean, that's the existence theorem here. That actually still holds even if you're not using power series, if you're using a slightly broader class of series, as we'll see at the end of class. But I need to work out one more thing by hand before I get out the projector, so let's do that. So there are 2 classes of problems in here in terms of series. The one is to be asked to find the first few terms in the solution. The first few terms in the solution problem, we just do what I've already done in class, which is to write it down and work it out. There's another kind of problem, which is to be asked to find the complete power series solution. This requires a little bit more skill. And you might have to work a little bit harder to get good at this part. Although I find that students who can do the kind of examples I've already done tend to not have trouble with the other one that I'm about to do. But I do admit it is a little bit more involved because it meaningfully interacts with the summation notation. So let me show you. So suppose we're trying to solve something like y prime prime plus x squared times y equals to 0. All right. This problem we cannot solve with our previous methods. All right. So here's the deal. We're gonna let y equals to the sum n equals 0 to infinity of a sub n times x to the power n. I'm going to work out the solution centered at 0 here. All right. If I do this, what's my y prime? I've got the sum n equals 1 to infinity of n a sub n x to the n minus 1. That's y prime. What's y prime prime? Well, y prime prime is the sum n equals 2 to infinity of n times n minus 1 times a sub n x to the n minus 2. All right? Uh-oh. Who's this?
This is Josh Cromwell.
Josh Cromwell. What? I'll take a...
Fist bump.
Do we do that? All right, I'll accept it. Very nice. I could tell stories about that student, but I will resist. That's fun. No, we have serious business to do. Yeah, pun intended. All right. No, I regret that. I regret it. Okay, so now we've got our three series. We plug it in. All right, plug it in. So I'll write it up here. Try to leave myself room. Y prime prime plus x squared y equal to a 0. So we've got the sum n equals 2 to infinity of n times n minus 1 times a sub n x to the power n minus 2 plus the sum, and I'm going to make a little bit of an algebra step right here, okay? N equals 0 to infinity of a sub n x to the what? What happens when I multiply my solution by x squared? How does that work? We add the powers, right? So if we multiply x squared into this, right? I'll do it over here. If I do x squared here, then that means that this ends up doing plus 2. All right? So I do plus 2 and plus 2. And that's all equal to 0. All right, so at this point, I need to bridge the... I've got apples and oranges here, right? I've got a sum over n plus 2 power, a sum over n minus 2 power. This guy starts at the level of constants, right? This guy starts at x squared. So these are only common when we're at quadratic order. So what we want to do in this kind of case is separate off the lowest two terms here, because they're exceptional cases. So I'll take n equals to 2, which is going to give me 2 times 2 minus 1, which is 1, a sub 2, like that, and then plus 3 times 2, a sub 3, and then I've got plus the sum, n equals 4 to infinity of n times n minus 1, a sub n, x to the power n minus 2. All right? And what I'm going to do next is I'm going to make a substitution to make both of these look the same. All right? So what I'm going to do is I'm going to introduce another variable in each case to relabel these sums so that they look the same. But the substitution I'm going to make is different for each one so that they meet in the middle. So like here, I'm going to let, let's say, j equal n minus 2. On the other hand, over here, I'm going to let my j equal to n plus 2. All right? So with this substitution here, that makes n j plus 2. With that substitution here, that makes n equal to j minus 2. Right? Notice that n equals to 4 implies j equals to what? Fill in the blank here. We want, well, if n equals 4, 4 minus 2 is 2. Right? Yep.
Wouldn't the A3 theorem have an X?
Yes. I thought, you know, it's like, I don't know if you guys watch Whistling Diesel or not. It's like that sign he has in the shop about like time since last accident or something. I need like one of those in here, but like time since last mistake, something like that. This is also a 2, right? Yes? No? Maybe so? Yep.
How did you decide that j equals n minus 2 and n plus 2 again?
Oh, because I want them to match. Because I want to be able to now, if I make that substitution, I've got 2a2 plus 6a3x plus the sum j equals 2 to infinity of j plus 2 times j plus 1 times a sub j plus 2 plus, oh my bad, x to the power j plus the sum j equals 0 to infinity of a sub j minus 2 x to the power j equals to 0. And here's the deal. The only way you can combine two power series is if they have matching exponents. Now that I have the same format here, I can merge these two into one big old power series. Let's see here, j plus 1 times j plus 2 times a sub j plus 2 plus a sub j minus 2, close parentheses, big power x to the power j equal to a 0. Yeah? Yep.
For the right side of the second to last one, shouldn't the j also equal 2 if we're going to combine them?
Thank you. That was a 2 as well, right? I just got done explaining why it was 2, and then I didn't actually write it. Oh, goodness gracious. You guys should ask for a refund. Liberty, I know Liberty and refunds.
Yeah, football game and a hurricane.
A football? We had a football game and a hurricane. Yeah, that sounds about right. Okay, so listen. As much as I love writing the letter J, and I'll write it one more time, this implies, among other things, that A2 is equal to A3 is equal to, you guys told me to write an X, and I gave you one of the X's, but I refused the second X for you. There it is. There you go. So A2 is equal to A3 is equal to 0, looking at coefficients of the constant in X. And J plus 1 times J plus 2 times A sub J plus 2 plus a sub j minus 2 is equal to 0. This is looking at x to the j for j equals to 2, 3. So equating coefficients of that equation gives me not 1, not 2, in fact, countably many recurrence relations, interlinking the coefficients. And I think at this point it is wise for us to change the letters yet again. And so what I'm going to do at this point is to go back to n, because my n is easier to read, you know? And like if I use the letter n for this, let this be n, then that makes n plus 2 equal to j, right? Okay, so if I use that substitution, what do I got? I got j plus 1 is what? N plus 3? J plus 2 is what? N plus 4, right? A sub j plus 2 is, a sub n, yeah, j plus 2 is n plus 4, plus a sub n equals to 0. Or if you like, and I prefer to write it this way, a sub n plus 4 is equal to minus a sub n divided by n plus 4 times n plus 3. This is for n greater than or equal to what? We already take care of 2 and 3 here, right? So we're talking about n greater than or equal to I think this is true for n greater than or equal to 0, actually, if you go back to the source here. Because this equation was for j equals to 2, 3, and so forth. So that makes n equal to 0. Yeah. So what this says is that my solution has some kind of interlinking every 4, right? And then past this point, you just have to kind of like work it out. So I'll start on that. Like if we look at a sub, 6, it's equal to what? Minus a2 over 6 times 5, yeah? Which is 0. And a sub 10 is minus a6 over 10 times 9, which is again 0, etc., right? In fact, anything of the form 4k plus 2 is equal to 0 for any k in there. See, the fact that the second one is 0 and the fact that they're linked every 4 by this, boxed, soon-to-be boxed recurrence relation makes all of these 0, right? If you understand this, the next thing is like pretty much the same song and dance. If I do a sub 5, which is minus, oh man, not 5, I want what? 7. A sub 7 is minus, I subtract 4 less than 7 is 3. A sub 3 over 7 times 6, which is 0. And then like a sub 11 minus a sub 7 over 11 times 10, also 0, etc. So what I see is that a sub 4k plus 3 is equal to 0 as well. All right? At this point, I have the good sense to get out the projector, so I'm going to do that. So, but if I had, unlimited time in here to fiddle around with things, what I would do is continue just sorting, like studying this recurrence relation, and we'll find a pattern that relates the coefficients. So notice what doesn't appear is a sub 0 and a sub 1. We can use a sub 0 and a sub 1 to formulate our solution, actually.